Hello students, welcome to Akshara 8 Foundation. So today we are going to discuss a new topic. So in the previous classes in volume 1, we have learned about the motion of the object and cause of the motion of the object. So cause of the motion of the object, we know that there is a force, okay. If the force is applied on the body, the displacement of the body means change of the position will be takes place, and that body has certain mass and it will be moved with certain acceleration there, okay. So then if the force is applied on the body means, so the body has certain work done. The body is doing some work there, okay. So then how that work can be defined? How the work can be defined scientifically? But in general cases, if you do some works, okay. So but scientifically the work cannot be done by a person there. So we have the examples like this. When a person is holding a suitcase in his hand and is standing at one place, then even if he stand up to the an hour, also there is no work done by that person, but there is a work done by the gravity. It will be there, but there is no displacement. No, so if there is no displacement, we cannot say there the work has done. Okay, so work has to be done means there is a certain displacement has to be there if the force is applied on the body there. Okay. So the work can be defined as, so now in this chapter, the chapter name is here work, power and energy. So here we are going to discuss about the work and then energy, then power, okay. So work, power, energy. So now here in this class today we are going to discuss about the work, okay. So then what is the work? What is the work? When the work done has taken place, when we can say the work has done by a body. So for this all the questions, we have the answer here, that is a work, okay. So work is said to be done when the body is undergoes a displacement, when the force is acted on the body there, okay. So if the force is applied on the body, then the body has certain displacement, then we can say that the work has done by the body, okay. The work has done by the body there, okay. So now here we have one example then. So if the force is applied there, okay, with certain angle, okay, otherwise we can see here like this. Suppose if an object is there here, so let us consider it is a block is placed on the ground, okay, and here a force is applied. This force is what there, pulling force is applied there. If the force is applied, this block will be have certain displacement from here to here. There is a displacement will be takes place on the body there, okay. The displacement of the body is there. So let us consider the body has a displacement like this. It has a displacement up to here. The body has moved there, okay. So now we can say that the body has certain work done. So there is a work done has taken place by the body there. Now here, so work done W can be given as here. Work done W can be given as, it is the product of force and displacement. Product of force and displacement. See here, force is applied in along the positive x-axis in one direction. In the same direction, displacement also it is there. So we can say that work done is nothing but product of force and displacement. Product and force and displacement. Okay. So then here we can say that we have said the definition of the work. What we have said there? So we have said that if the force is applied on the body there, okay, when a force is applied on a body, if it is undergoes a displacement in the direction of the applied force, then we can say the work has done there, okay. So that is called work. So work is also defined as product of force and displacement. It is also defined as product and force and displacement. So here it is said, see here, work is said to be done by a force if point of force or displaces the body. Application of force undergoes a displacement. Here it is there, it will be go the displacement, it has the displacement, then we can say the work has done. So now here in this example you see there, in the previous example we have seen there, the force has acted along the horizontal direction. The force has acted on the body along the horizontal direction. But here the force is acting certain distance, certain angle with the horizontal. So in that case, so what is the work done? Okay. So what is the work done? So this is a practically in which case we can see there. Suppose an object is tied with the string, okay, an object is tied with the string of one end, another end is in our hand there. So then we can get the same example there. So there the string will be have the certain angle with the horizontal and the body can be moved there. So now here, like previous case, it is not like that there. The force is applying certain angle, along certain angle, but the displacement is so along the horizontal direction. So in that cases, in this case, then what is the work done? So in the what we have said there, the work done is nothing but if the force is applied there, point of force applied on a body, and by that point of force, if the body is undergoes a displacement in the direction of the applied force, then we have said there the work done. But here it is not like that. If the force applied here, the force applied at certain angle with the horizontal, then the displacement is along the horizontal direction. There is no displacement along the applied direction there. So in that case, how can we define the work done? Okay. So now in these cases, in like these cases, we can see the work done. So now applied force along the string by our hand. Okay. So now we have to take the component of that force along the horizontal direction. We have to take there component of this force. So how can we take the component of that force? Will we see here? Okay. So component of force we'll see here like this. See, suppose the body, this is an object there. Let us consider it is a brick. This is a brick there. Now the force has applied like this with certain angle here at certain angle with the horizontal. This is a horizontal and the block is there on the floor on the ground. Okay, now it is making an angle theta with the horizontal there, and there is a displacement. The body will be have the displacement along the horizontal direction. The displacement is not along the direction of the applied force there. Okay, so now in these cases, so we have to take the component of this force. So how to take the component of force? We have learned in the vectors there. Component of this force. Okay, it is making an angle with angle theta with the horizontal. So how to find out the component of that? So we have to draw a normal line from this vector onto the horizontal, so that we'll get a right angle triangle. Then apply here. So apply here cos theta. So now this horizontal component can be represented by fx. Okay. So now cos theta is nothing but what there? Adjacent by hypotenuse. No. So then here we'll get there fx divided by f. Then here fx can be written as f into cos theta. So now, so to find out the work done in this case, we have to take the component of this force, which is applied on the body. So horizontal component of the body, that is fx, has to be taken there. Now the work done can be written as here w is equals to fx into so displacement. What is the displacement here? This s displacement is taking there. So s displacement. So if the force is applied there, the block may become up to here. Okay, the block may become up to here. So like this, the displacement of the body may be there. Now here w is equal to fs into, so fx into s, it will be there. So now here we can write the equation of the work done. So w is equals to f cos theta. Fx is nothing but what we got there. It is a f cos theta. So f cos theta into yes displacement we can write. So therefore w is equals to, we can write here w is equals to fs into cos theta we can write there. So this is the expression for the work done in the case of if the force is applied on the body at certain angle with the horizontal. Okay. So like this we are going to see there different cases, okay, in the next, and we'll see here now this one. Okay, so same formula we got now here, w is equal to f into s cos theta. We know that vectors in the previous class, in the volume 1 we have discussed about the vectors there. So if it is the fs cos theta, then fs cos theta is nothing but what there. So dot product of the force and the displacement will be there. So we can write, so w is equals to f bar dot s bar also we can write there. So work done is also defined as the product of dot product of force and displacement vectors. Okay, so one more definition, we can define the work done in the vector form. Okay, by the vector concept also we can define, that is the dot product of force and displacement of a body is also called as work done, is also called as work done there. Okay, so now suppose the displacement, here we have seen there the displacement is moving along the horizontal direction, but the force is applied so with certain angle there. Okay, suppose if the displacement is along the this direction and the force is applied along the horizontal direction, in those cases, suppose here we can see the example like this, we can see the example like this. So if the a body is there, okay, we'll see, we'll take like this. So there is an inclined plane of inclination theta is there, here the body is there, here the body is there, and the force is applied here and it is moving, it is moving there. Okay, so in these cases, so here how the work done can be taken. So the weight will be acted downward direction, W is equals to mg we can write here, always weight of the body will be acted downward direction, and here this will be the theta we can take here, and this is a mg cos theta we can write here. So component, horizontal and vertical component, resolving of this vector weight is dividing into two components. This is mg cos theta and here mg sin theta, mg sin theta, mg sin theta. Okay, so now it is moving on this inclined plane of distance here, suppose if it is L there. Okay, L. So now work done by the body here. So work done by this force, what can we write here? W is equals to, so force F into here displacement L we can write there. What is the force from this? So this force, it is a F no horizontal. So F is equals to, we can write here mg sin theta we can write here, mg sin theta. So then W is equals to, we can write here, so mg sin theta into, so L we can write there, L. So then W is equals to, we can write mgl sin theta, mgl sin theta. W is equals to mgl sin theta we can take. This is another case like this. See here, it is moving on the inclined plane, it is moving on the inclined plane. So then work done can be written as here mgl sin theta. In the previous case, what we got there? We got this is work done by the gravity there. So work done by the gravity, here the gravity is, weight of the body is acting downward direction, the block is moving along the vertical direction. So we can write here work done by the body, parallel to that it can be taken as work done by this body, work done by the body upwards, sliding up, this block is moving upwards, then we can write here mgl sin theta, and if it is moving downwards there, then we can write here negative. Okay, so now here we can see this one. Yes. So next concept here, work done by the constant force, work done by the constant force. So if the constant force, in the first example we have seen, no, on a body if the force is applied there, then the body will be moved along the direction of the applied force. Okay, then we can say simply the product of force and displacement is said to be the work done, we'll get. Okay, so now we'll discuss next concept, the same example here. Then when this work done, okay, when this work done will be maximum there, same example we have seen, if a body is there here, then component of this F force is F cos theta, and displacement is here it is taken D there, D displacement the body has taken place. So now the force can be written as here W is equal work done is equals to force into displacement we can write there. Okay, so now we'll see there in what units the work done can be measured, in what units the work done can be measured. So work done can be measured in the, by the formula, work done formula, what we get there, W is equals to force into displacement, now force into displacement. Now force will measure in here newtons, force will measure in newtons, and displacement will measure in meter. The Newton meter will be the SI unit of the force. Okay, so then Newton meter is nothing but joule. So the Newton meter is nothing but, we can say here, joule. This is a Newton and meter. The Newton meter is nothing but joule there. Joule is a scientist name. To honor the scientist, the Newton meter is given as the joule there. Okay. So how can you define this joule? So when 1 Newton of force is applied on the body, 1 Newton of force is applied on the body, if the body undergoes a displacement of 1 meter, then we can say the work done by the body is said to be 1 joule. Work done by the body is said to be 1 joule. Okay. So if 1 Newton of force is applied on the body, then the body will undergo the displacement of 1 meter, then the work done by the body is said to be 1 joule. That is a definition of joule. So joule is the SI unit of the work done. Joule will be the SI unit of work done. And here now CGS unit, and we have the relation between this joule and CGS unit is here. CGS units is nothing but dyne centimeter. Here CGS unit is there, see. So that is the dyne and centimeter. So CGS unit of force is nothing but dyne, and the displacement, CGS unit of the displacement is centimeter. So dyne centimeter is nothing but erg. Dyne centimeter is nothing but erg, will get there. And here we have the relation between joule and the erg. So the relation between, in 6th class we have learned about the dimensions, like how can we convert a system of units, one system of units into other system of units. Okay. Here, so we will get the relation like this, 1 joule is equals to joule and the erg. So we will get the relation here, joule is nothing but what there, Newton meter. Newton is nothing but what again? So kg meter per second square and meter. So kg meter square second square will come there. Kg here, this Newton is nothing but kg meter per second square, and again into meter is there. So kg meter square per second square is there. That is the Newton. That is joules. Okay, that is a joule there. Now here dyne is nothing but gram centimeter per second square. Again here centimeter is there. So gram centimeter square per second square will come there. So now this SI units. So kg meter per second square. Kg meter, if we convert into the CGS units, grams and into the centimeters, then we'll get the erg there. CGS unit will get there. So now, so if you do there, we know that 1 kg, how many grams there? 1000 grams, and 1 centimeter, 1 meter, 100 centimeters. So if you write those two here in the SI units, then the joule can be converted into the erg. So after substituting the 1000 and here 100 in the SI unit, so we'll get there 10 to the power of 7 erg there. So 10 to the power of 7 erg. So I'll show here in the board. See here. So 1 joule is nothing but what we have said there, Newton meter, no? Newton meter. So now here Newton is nothing but what there, kg meter per second, kg meter per second square, kg meter per second square, kg meter per second square, into meter is there again. So we'll get here kg meter square per second square, kg meter square per second square. This is what there, it is a SI unit. This is a 1 joule. This is a 1 joule. This is a SI unit. It will be the SI unit now. Okay. So now see here, convert this kg and meter into the CGS units. So we know that this can be written as here 1000 grams. No, okay, 1 kg is 1000 grams, and 1 meter is what, 100 centimeters. 100 centimeters whole square. Here square is there, we should do whole square there. The centimeter square as it is here, per centimeter square is centimeter second inverse 2. Okay. So now here how much we get there? This is a 1000 grams, and here 100 whole square means here we'll get there 100 into 100, 10,000 will come there. 10,000 here we can add there, 10 to the power of 4 we can add, and centimeter square into second inverse 2. So now here we can add that this 1000 means 10 to the power of 3 we can add here, into 10 to the power of 4 we can add. So it will become gram centimeter square per second square will be there. So it can be written as here now 10 to the power of 7 gram centimeter square per second square. So this is called here erg. So that is equals to here 10 to the power of 7 erg we can write erg. So since So erg is nothing but erg is equals to gram centimeter square per second square. Okay. So therefore, we'll get the relation between the joule and the erg. It is 1 joule is equals to 10 to the power of 7 erg. Okay. So that we'll get from here. See here. So the relation here we got there. Joule is equals to 10 to the power of 7 erg. How we'll get there? If we convert these SI units into the CGS units, the values of SI units into the CGS unit, then we can get this relation. Joule is equals to 10 to the power of 7 erg. Okay. So now next we'll see here, we got the formula of the work done. We got the formula of work done now. So that is Fs cos theta we got there. So then when this work done will be maximum, minimum, what are the types of the works we will be have there, that will be see in the okay, later we can see there.